Today you will learn about how you can simplify a set of forces and couples or moments on a body down to something that is equivalent but more simple. In the figure, you notice that there's a yardstick being held out by a person, and imagine two forces F1 and F2 applied to that yardstick. It turns out we can come up with an equivalent load that causes the same effect on the stick as a body as those two loads. And typically it will consist of a single resultant force and a moment. So after this lecture, you'll be able to determine the effect of moving forces and find an equivalent force couple system for a given set of forces and moments. As usual, there are example problems and group solving problems you should go through by downloading the slides or opening them up on the course website and following along those examples as well as the examples that I record for you. So if we move a force, what happens? How does that change things? What does it do to the body? We're more interested in external effects on the body instead of internal. What do I mean by that? Well, if you push on, let's say, your car, okay, so imagine you're pushing your car, you ran out of gas or it broke down or whatever, you've got to push it off to the side of the road. It doesn't really matter if you push the car on the left-hand side of the trunk or on the right-hand side, right? You can get it to go forward and move into place. But it may make a difference if you push on the trunk itself or on, say, the tail light, right? The tail light might break. The tail light is a weaker material. It's made of plastic, whereas the trunk is often made of metal. And while the trunk can deform, if you deform the plastic too much, it will break. It doesn't have the same strength that the metal has. So the internal effect, the way that the stresses distribute throughout the body, is not the topic of this class. That's the topic of strength of materials. But depending on where you apply your force, the internal effect, the stresses inside of the material, will be different. We don't care about that. All we care about is the fact that it doesn't really matter if you apply force at one side or the other, you'll get an equivalent result. Now, that's not exactly what we mean by an equivalent force system, but hopefully it gives you the idea. So the question is, how do we do this? How do we determine the effect of moving a force, say from one end of a stick to the other, or taking a force that is perpendicular to the stick and bringing it back towards the hand? How do we figure out exactly what would be an equivalent set of forces and moments? And we always combine the force into a single force, but what would be equivalent to the initial scenario? So you see the initial scenarios on the left-hand side of this these pictures, and on the right-hand side is the equivalent set. Often, and unfortunately some of this kind of ties into the strength of the materials, but often what you need to do is calculate the effect of forces at a different location on the body, because what you want to do is you want to remove the majority of the body, at least cognitively and theoretically, and see what the loads that actually exist on that part you remove, what are they doing in another part of the structure? So a common problem is, how do I figure out the size of fasteners to hold this column down? Given that this is the design of the column, there are some force loads on it, how do I figure out the bolt sizes necessary to support this thing and resist these loads? Well, it's easier conceptually to basically think of removing the I-beam portion of the column and having some equivalent set of loads applied at O, at the plate itself, so that you can then move forward and determine the fastener size required to hold the plate down. So we need some equivalent set of loads at O that will do the same thing to the plate that this overall beam with the loads at the top of the beam are doing to the plate. And so that's a main reason for doing this. So how would we do that? How would we go from, three loads, we've got F1, F2, and then a moment, M. How would we go from that to, say, one equivalent force and one equivalent moment at O? Because what that allows us to do, even though it's not shown here, is just neglect the I-beam. It doesn't matter anymore, and we can work with just the plate. So that's another application of these concepts. So how do we do this? Well, first things first, is that you got to remember the forces are going to tend to cause moments. So usually what you're trying to do is move these forces and moments to a particular point. So you've got a particular point. In the case of the beam, that point was at the plate, and we had a reason for doing it. But sometimes you move the forces and moments to a point that's a joint in the mechanism, like a pin joint or something. But we're looking for the resultant force and moment that will give the same effect on the body. Now remember, it's an external effect. Obviously, if you think of this as a fluffy cloud, okay, maybe we make it out of cotton and we apply the force F1 and F2 where they're actually shown in the first figure, and we apply a moment down at the bottom. If the body's deformable, there's going to be a totally different effect on the body than applying a single force at O and a single moment. But remember, in this course, we're dealing only with rigid bodies. So we're assuming that the bodies do not deform at all. And so it doesn't really matter where we choose to apply our equivalent force and moment in terms of the effect on the body, the external effect, the way the body remains in equilibrium. Obviously, it affects the internal stresses in the body. And the nice thing about this is we can choose any point we like and find an equivalent force and moment at that point. Now, that moment will be different depending on what point you take, but the force itself will be the same. You'll see why that is in just a moment. First of all, let's consider moving a force on its line of action. So if you've got a force out at the end of a stick, let's say, and you think about what's going on at the hand, well, the stick is pulling on the hand, right? So the force that the hand sees is equal in magnitude to the force at the end of the stick. And so the hand pulls back with a force negative F. So the effect, if you think about it, as far as the hand's concerned that's holding the stick, it just feels like there's a force F acting on the stick that you have to resist, right? It's the same effect on the body. So you can take a force and move it along its line of action freely, and it will have this same effect on the body as the force in its original location. So we call this force vector a sliding vector because you can move it. Now, obviously, if you, in the real world, apply a force at the very end of the stick, there's going to be stress along the entire length of the stick, whereas if you move that force closer to the hand, and say somebody else is moving their hand, they're applying that force, so they move their hand closer to yours where you're supporting it, obviously the stick that's out beyond the second hand has no stress in it. So the internal effect is different, but the external effect is exactly the same. Now, if we move a force off of its line of action, then we have to add in a moment. So if you should take a pencil in your hand or a ruler or whatever you have there and hold it and feel what it feels like to put maybe a constant weight at different points along the length of that line. Let's try. Let's see, what have I got sitting here? Something to make the house smell good, okay? So you can feel the effect of putting this force at different locations. What you notice is that the twist, the amount of twisting that this load does, is much greater here than it is here. When you move the load closer in to the point of support, my hand in this case, the moment decreases. And so if we're going to move this force in, we have to add in a moment in order to have an equivalent effect on the hand, okay? So if we move this force from the end of the stick all the way back to the location of the hand, we have to add a moment equal to the moment created by the original location of the force. In other words, D times F, in order to have an equivalent set of, force and moment on the hand. So when a force is moved off its line of action, there is a change in the external effect, and so we have to add a new couple or a new moment in order to have an equivalent set of forces and moments to what we had in the beginning. Now this couple, this moment, can actually be applied at any point on the body without changing the effect on the body at all, and so it is also a free vector. Normally, though, we think of it as being applied at the support where, at O, if you will, at the location where we want to find an equivalent set. But it turns out it doesn't matter what point you take on the body, the equivalent moment will always be the same amount. So what's being done in this figure is a given set of forces, F1 and F2, with a moment, and unfortunately they call it MC. I wish they'd give it a different name because it's going to be a little confusing. But this moment, we'll call it MC for now. These are the loads actually applied to the body. And the body's just some generic body, but it's a rigid body. And what's being shown is you can take those forces, F1 and F2, move them off their line of action, but when you do that, you have to add a moment. So, for example, for F2, when you move it off its line of action, you have to add the moment that it was causing, M2, which is equal to R2 cross F2. And when you move force 1 back to point O along line R1, you have to add a moment M1 equal to R1 cross F1, referencing the figure. Since MC is a moment applied to the body, it is a free vector. You can move it. Now, you can't change its orientation or its magnitude, but you can move it to any point you like. And so moving it to point O is free, essentially. Then from that, what we can do is simply add up all three moments, M1, M2, and MC, and come up with an equivalent moment, and then add all the forces together to come up with a resultant force. And now we've got an equivalent force couple or force moment system to the original set of forces and moments. In this case, we just had one moment, but there could be multiple moments. And all you do is add the moments together, move them wherever you like, because moments are a free vector. So once we've done that, what have we really done? Well, this is what we've done. You'll always end up with a resultant force that is simply the sum of all the forces on the body. It's that simple. So whatever forces are acting on the body, or that you're considering in this free body, those forces just add up to a resultant force. Now, what about the moment? The moment is easy on one hand and difficult on the other. The moment's easy because any actual real moments that are applied to the body can simply be moved wherever you like. And that's actually the last term in this equation. It says plus the sum MO. And I wish that they had somehow called MC in the figure MO. All that second term really means, sum of MO, what that really means is just add up all the moments, okay? Just add them all up, and that's going to be one of the terms in your equation for your resultant moment. The first term, sum M sub C, this is why I don't like that they called it MC, but this what it really means is add up the moment caused by all the forces, all of the couples. That's the way I interpret the equation. That's the way I want you to interpret it, because I think it's a clear understanding of it, and I think that's really what your book intends. But anyway, basically the first term is recognizing the moment caused by all of the original external forces, and the second term is just the sum of all the original moments that were on the body. And so this allows us to calculate a resultant, or add up all the forces, and a resultant moment, not just adding up all the moments, but adding the moments plus the moment of the forces, so that we get an equivalent moment and force system from the original set of forces and moments. It's really a simple concept. I'm probably not describing it to you very well, but once you've seen a couple of examples, I think it'll become pretty clear. Now, often we deal with two-dimensional problems where there's not a third dimension that is significant to consider. If that's the case, then you don't have to use a complete vector equation set like we had in the last slide. Instead, you can use these three scalar equations where you have a resultant force in the horizontal direction, a resultant force in the vertical direction, y, and a moment result, an equivalent moment. But this equivalent moment still comes from the moments that were originally applied plus, well, I should say it the other way around, the moment of the forces originally applied plus whatever pure moments were originally applied to the body. And the nice thing about this is that the direction is taken care of, because in two dimensions, you're going to have an x and a y, and then the moment is out of the plane. It's perpendicular to the xy, and that's it. That's all you can have. So if you're dealing with a 2D situation, the vector equations simplify down where we can just use three scalar equations. Now, it's also possible to simplify things down even further. There are some special situations where you can do some interesting things. So, for example, if the resultant force that you calculate and the resultant moment are perpendicular to each other, then you can come up with an equivalent resultant force and move it from one point to another in order to, how can I explain this? It's so that that resultant force causes the same resultant moment from the original, but you end up with only one resultant force. This is sort of a red herring, so to speak. It's not something that is absolutely critical to the course. If you understand it, great. If you don't worry about it. It's just kind of interesting how far you can simplify things down. So there are special cases where you can simplify things further than in the general case, and that's one of them. So if you end up calculating, your resultant force and your resultant moment as shown in the figure here, and you notice that the two are perpendicular to one another, then you can move the resultant force away from O. You can find some point P such that you move the resultant force to that point, and all you need is the resultant force. You don't need a resultant moment because that force has the appropriate moment about O. So it's just something interesting. There are other cases as well, and there are three special cases. There's concurrent. What do we mean by concurrent? Well, if all the forces pass through a single point on the body, then those forces are concurrent. And in that case, you will always be able to reduce the entire force system to a single force, regardless of any moments. You'll be able to reduce to a single force, move that force to an appropriate point, and come up with the, an equivalent moment because of the location of the force. If the forces are all coplanar, in other words, if they all lie in a single plane, the system can always be reduced to a single force. If the forces are all parallel, which is actually the example shown here, again, the system can always be reduced to a single force. But don't worry too much about this slide. It's just an interesting footnote and not something that I expect you to use in exams and things. I might have some homework on this. You might do something in a project related to this, which would be interesting. But these are just special cases. That's all they really are.